Hello, my name is Peter Voorhees, and I would like to welcome you to the CHiMaD Annual Meeting 2020. I'd also like to welcome you on behalf of my co-director, Juan DePaulo from the University of Chicago, the Chief Materials Designer at CHiMaD, Greg Olson, and the Associate Director of the Center, Begum Golsoy. So why are we here? What is the objective of CHiMaD? And that is to focus on this major challenge of materials development. And the challenge of materials development is well illustrated by the development of high-performance aluminum alloys. The first high-performance aluminum alloy was created in 1903 by the Wright brothers. It consisted of aluminum and copper. Copper was there to strengthen the alloy. About 100 years later, the commercial alloy that is widely in use these days is aluminum 319. And you can see it still shares the legacy of the Wright brothers, but it has many other alloying elements as well. And if you look at the long list of elements here and the 4 digits of precision that people use to specify the composition, you can see why it took this many years to develop this material. In the functional materials area, Exxon was working with lithium-ion batteries in the 1970s, but it wasn't until the early 90s when Sony was able to actually commercialize this and bring a lithium-ion battery to commercial practice. And as you know, lithium-ion batteries are still under development, and in particular, this is an example of lithium-ion usage in automobiles. And so the development of lithium-ion batteries started in the 70s and is still continuing some 50 years later. And so the question we're focused on, or the issue we're focused on, is how to reduce this long cycle. And the reason for this cycle is quite clear, is because the way people typically develop materials, and that is you choose an alloy composition, then you choose a processing path, you build it, test it, and inevitably you do not get the properties that you wanted when you first chose the alloy composition, and so you go around and around in this circle until eventually you get to the properties you want, and this is extremely expensive. And it's a huge barrier to the introduction of new materials, as I just illustrated with the aluminum alloys and the lithium-ion batteries. The other problem is well illustrated by the aluminum alloys, and that is that in many cases you have to worry about certification. And what that means is that even if you wanted to change the composition of the, let's say, aluminum 319 a little bit, you would have to recertify the alloy, and this is extremely expensive and very time-consuming. So one way of breaking this very invirtuous cycle was presented in 2011, and it was the Materials Genome Initiative for Global Competitiveness. And the idea there is to use this materials genome approach to develop advanced materials twice as fast and at a fraction of the cost. And how do you do that? You do that by integrating experiments, computations, data, and nowadays machine learning in order to develop these new materials. One of the key aspects of it is it must be open access and open source so that everyone can take advantage of the data and the codes and the design tools that are available. And it has to be a national initiative where you develop an infrastructure throughout the country, as well as to educate new materials designers and how to use these new computational and experimental techniques. And the ultimate goal is a design paradigm where the material and the device is designed at the same time, simultaneously. And what this means is that the challenges associated with materials design, the risk associated with materials design is balanced against the risk associated with the actual mechanical or electrical design of the material, of the device. So in order to realize the vision of the Materials Genome Initiative, the National Institute for Standards and Technology stood up their Center for Excellence in Advanced Materials, and this is the Center for Hierarchical Materials Design. It's a joint project between the University of Chicago, Northwestern, and Argonne. Questech Innovations is a small company in Evanston that's focused on materials design and very helpful for us in the later stage development of materials, the higher TRL levels. And the ASM Materials Foundation helps us with our outreach. So to give you a brief snapshot of what we've done in 2019, lots of papers and presentations over the past year. 2 patents were awarded and 1 was filed. The materials data facility, which I will discuss later, is now used as a framework for 2 new community databases. We've won numerous awards. The faculty and the PIs involved have won numerous awards. These are just a few of the prestigious awards that the PIs have won. And we're collaborating with a large cadre of NIST researchers. And so there's a large fraction of people at NIST that are equal in size to the ones here in CHiMaD that are essential in the development of new materials and achieving our goals. So how do we achieve our goals? And this is a relatively busy slide, but I just want to try to outline a couple of things. Down in the bottom here in brown boxes is data. In the middle here in the green boxes are tools. And up here is the design process. And the important point here is that the data and the tools flow upwards to help you do the design at the early stages and late stages, the later stage TRL levels, in order to get the materials out into practice. Here, what you're trying to understand is the effects of the materials properties due to the large scale production. Here, you're trying to isolate or identify and isolate the prototype necessary to get to the scale up. But they all are designed using these same sort of principles. So to do this design, we bring together experts across a range of disciplines and use cases. And these topics of interest are in the use cases are suggested by NIST or industry, for example, the design of material of a certain type. They use, the use cases use databases or create them. They use the tools that are being developed here in the CHiMaD, machine learning, phase field, and uncertainty quantification, as well as others. And they use these tools to design a prototype, which then we use the same material, the same computational methods to insert these materials into practice. The other important aspect of the use case groups, beyond being interdisciplinary and using all of these various inputs to design materials, is that we train people and transfer these concepts to the workforce, and that is the best way to transfer intellectual know-how to industry, for example. To give you an idea of what a typical use case group looks like, this is two-dimensional electronic inks. It involves PIs from Northwestern and the University of Chicago, as well as a large cadre of NIST PIs. And we wanted to demonstrate that this materials genome initiative could be used across all materials. And so we have use case groups on structural materials, functional materials, and soft materials. We have cross-cutting design tool groups. And down at the bottom here, which is because the basis for all of this work, is data. And I'll talk about the databases and our work on machine learning and artificial intelligence. So in the structural materials area, we're working on alloy designs for additive manufacturing, carbon reinforced composites, and cobalt superalloys. And the focus on additive manufacturing is really on the development of alloys that can take advantage of the unique thermal characteristics of additive manufacturing, very high cooling rates, very high solidification rates, to enable these unique devices that can only be made when you're basically building the material one layer at a time. And in this example of an alloy design process and our close interactions with instruction, Greg Olson in his MIT design class this past year focused on the design of a printable an alloy that can be used in additive manufacturing, precipitate strength and shape memory alloy. And using the property objectives here, strength, the shear modulus, and yield strength, and characteristics of the solidification characteristics, such that you don't get hot cracking, they were able to pick a region in composition space here that the design says should satisfy all of these objectives, as well as the processability to give you this precipitation strength and shape memory alloy, and it's given here. We're looking at cobalt superalloys for high temperature use, and here the idea is to go to use a higher melting temperature of these cobalt superalloys to enhance the efficiency of turbines for either aircraft or land-based applications. And the focus here is to focus on the precipitates, which are gamma prime precipitates, their dissolution coarsening process, as well as the oxidation process on the surface, which is an extremely important part of these cobalt superalloy development process. And every use case group has a design chart that looks something like this, where processing structure properties and performance are linked together, and what goes into these boxes is unique to every use case group. And so this is the cobalt superalloys group, and so they're worried about casting or a selective laser melting. This is an additive manufacturing example where we take the results and we interact with the additive manufacturing use case group I just showed you before, the results from this use case group. But you use the processing and the casting, and the processing leads to the precipitates of given sizes, the mechanical properties, and that gives rise to the performance you need for a particular application, like the oxidation resistance, deformation or creep resistance, and the aging resistance of the precipitates, or the coursing resistance. The carbon reinforced composites group is interested in cryogenic liquid storage. This is a project that was suggested to us by SpaceX, but other applications include infrastructure and body armor protection, body armor or armor for cars. And the idea is to choose a polymer and fillers, and by this processing, the layup process, alter the structure, give you the mechanical properties you need that give you the properties, mechanical properties such as the stress, the ability to withstand extreme low temperature behavior associated with cryogenic storage, and a response to, for example, electric fields. This is important when you use these in applications, for example, in aerospace. And so what the group is focused on most recently, for example, is how you deposit cellulose nanocrystals, and how these cellulose nanocrystals can be deposited in a way where you understand what the modulus of the surface layer and the viscoelastic properties of this layer are. And in order to guide these experiments, there are coarse-grained molecular dynamics simulations of polymers that are grafted to these cellulose nanoparticles. And using this insight, you can understand how to process these materials to give you the properties that you need. In the functional materials area, we're working on thermoelectrics and two-dimensional electronic inks. And thermoelectrics, I think, are well known for having a whole raft of important potential and actual applications, from electricity generation in spacecraft applications, cooling in seats in cars. But if these thermoelectrics can be better engineered, you can think about possibilities of waste heat recovery and other things. And so the focus of this group has been twofold. One is to focus on grain boundaries and interfaces to understand how these affect things like the thermal conductivity and the thermal diffusivity in the material, both in terms of twist boundaries, the actual boundaries, the structure of the boundaries between two crystals. We've also worried about what the effects of graphene and the graphene boundaries are on the scattering, and hence how that affects the thermal properties. But they're also working on materials discovery, and here you're using density functional theory to identify compounds of particular interest to thermoelectrics. And here they're looking for low thermal conductivity compounds using this materials discovery in the Open Quantum Materials database, which I'll talk about in a second. Functional materials, we're also looking at two-dimensional electronic inks, in this case, printable low voltage transistors. So the idea here is you have inks with 2D materials in it, and you use an inkjet printer to print electronic devices on, for example, flexible substrates. And the idea is to use computational searches and optimization to understand what the solutions you need in order to be able to process these using, let's say, for example, moly disulfide, which is a standard 2D material. And you're focused on maintaining high electrical conductivity using the chemical composition and layer thicknesses in order to produce these inks. And this is indium selenide, and that's tungsten disulfide. In the soft materials design area, we're looking at directed self-assembly, design and properties of polyelectrolyte complexes, and high performance impact protection. The directed self-assembly is focused on making ultra-fine lines on surfaces for micro or nano electronic applications. And the challenge here is to make these lines at a very, very small pitch, on the order of 16 nanometers spacing, and do this over enormous areas necessary to build up microelectronic devices. And they're doing this by using a combination of simulation that is informed by experiments using artificial intelligence optimization processes that allows you to model the phase separation process to give you the block, to give you the phase separation necessary to give you the lines, but it's informed and tested by experiments. And so the X-ray metrology is an important part of this effort too. And so in the past year, they've achieved a 14 nanometer pitch with the right very low defect quality, but they're also pushing it to still smaller levels. This is an 8 nanometer pitch working with Seagate, for example. And they're also looking at three-dimensional self-organization processes using blue crystals and three-dimensional architectures. As I said, soft X-ray probes or X-ray characterization is an important part of this use case. The other soft materials design use case group is looking at polyelectrolytes. And here, these are novel polymers where you use the charge associated with the polymers to give you another degree of freedom, another knob to tune the properties of these polymer systems. And so by looking at the electrostatics, you can basically change the properties of these polymer mixtures. And so they also have a design chart. And it shows that by varying the processing structure and properties, you can look at performances that range everything from drug delivery to adhesives to tissue scaffolds by varying things like the pH, which varies the electrostatic interactions, to the toughness, to the characteristics of the polymers themselves, the polyanion structures. The high performance impact protection group is looking at novel ways of channeling energy associated with impacts to regions of a helmet or another device that avoids the problems with the impact being absorbed by a human, for example. And they're doing this using two ways. One is that they're designing new network materials using computational methods, and also looking at the interaction between a larger particulate, and a fluidized bed where you have particle and fluid in a substrate on which this particle impinges. And so the network-based metamaterials are focused on designing materials that have negative Poisson's ratio. These are oxidic materials where you push on them one way and they contract rather than expand like you might expect. And this is done by simulation, but they've also been able to show that the experiments find very similar behavior to that predicted by the simulations, calculations. And they've also been focused on high-speed impacts, using to focus on the impact of a particle in this fluidized bed, and they can get up to strain rates of 1,000 per second or 10,000 frames per second, which is really quite an achievement. We have a number of design tool efforts in the center. One of them is phase field methods, and the phase field methods are being integrated through all the work in the center. Some of the other use cases use phase field methods. But here what I'd like to focus on is the community building aspect of this phase field methods group. And what we've done is stand up the phase field community hub, which is a website to which people can post their phase field codes and the performance of those phase field codes. And we're measuring the performance against benchmark problems that people can test their codes against. And so, for example, spinel decomposition is one benchmark, and we've had 54 uploads and 4 variations of the problem suggested. Same with elastic precipitates, for example, 12 uploads and 8 variations. And this has been very helpful for not only understanding existing codes, but it's been also helpful for the community to develop new ones. And one example of this is Sandia National Labs is developing a phase field code, and they were able, by using this phase field community hub, they were able to get their code running faster and in a more accurate way than they would have otherwise. The uncertainty quantification is a very important part of the center, because when you're designing material, you have to know the uncertainty associated with predictions from a simulation or uncertainties associated with the experimental data and how that propagates down the line with your designs, and how much uncertainty you have in the end design of your material. And so this is using Bayesian frameworks that allows basically to understand experimental data, to use the uncertainty in experimental data to understand the uncertainty in the model parameters. And it's very easy to use this in a cyclical way where you can come back and modify the Bayesian method to understand exactly what the model parameters are and their uncertainty. This is a new group that's become very important in the past couple of years since we started in the second iteration of the CHiMaD. Materials informatics is essential because materials design rests on the foundation of data. And so here's the data that sits down at the bottom here, and this data propagates upwards to feed virtually everything else in the center. And so we have to have an important part of the center in the materials informatics space. And we're doing this in a number of ways. The first one is by databases and making these databases open source, as I mentioned at the beginning. That's a very important part of the Materials Genome Initiative. And one of them is the Materials Data Facility that I mentioned earlier, where you can it's open source and you can publish data both large and small, but you can get credit for it. You can assign a digital object identifier, which allows people to cite your data sets. And what this enables you to do is to build up a community of people using your data. And we have, as I said, 2 examples of that recently, just this past year. Another important database for the soft materials area to enable soft materials design is one in which we're looking at the thermodynamic properties of polymer blends through the Florey-Huggins parameters or glass transition temperatures. And there are now more chi parameters in the polymer handbook than in the polymer handbook. And we're using natural language processing to help extract these Florey-Huggins parameters from existing literature. The Open Quantum Materials database uses density functional theory to calculate properties of materials, both hypothetical and real. There are over 630,000 materials that are now in the database. And what this enables you to do is to train your machine learning algorithms, for example, and understand and search very quickly for materials that might be of importance or interesting for a particular application or phase diagrams. One of the big challenges of CalFAD modeling, which is a way of modeling phase diagrams and extracting free energies that are usable in other applications, is the idea of data. You need data to create these models of free energies. And so we've created a database that collects that data and enables you to start doing CalFAD assessments in a much faster and easier way. And this is in a collaboration with Carrie Campbell and her group at NIST, and they use the materials data creation system. And right now it has mostly diffusion data and some thermochemical data for various systems, but it's one of the most comprehensive solid state diffusion data repositories in the world. So the artificial intelligence and high performance data mining group uses this data. And the idea is to use state-of-the-art machine learning algorithms to data-driven informatics. It helps us both with understanding how processing connects with performance and how performance connects with processing, and develop this software and deploy it to the materials community. And this stretches across all of the use cases. In fact, we can't even begin to mention all of the artificial intelligence work and all the use cases. And so this is just a small amount of the work that's ongoing, but even this is quite substantial. And so what we've done is we've looked at deep learning algorithms on the energy of formation that is predicted by the Open Quantum Materials database. And what this is really, I think, an important development because it addresses the big critical issue of materials data, and that is that materials in general does not have big data. And how do you use deep learning algorithms that require big data on materials data sets? Using conditional generative networks, neural nets, you can create microstructures that from a 2D section that is used to basically to do representative microstructures of various materials, in this case, high carbon steels. And we've had for a long time a very nice model of fatigue strength of steels using CalFAD-based modeling along with data from the literature. And these are just three of many, many others. And you'll hear about this in the artificial intelligence and machine learning talk that's been posted on the web, as well as during the meeting itself. Outreach is a very important part of the center. And so we're doing materials design training for industry in this case. And we have a set curriculum now that these are our trainers that go to an industry or a company and bring teams together to train them in how to do materials design and enhance or reduce the time required to insert new materials. And so this is ongoing, and we're going to be doing it now virtually in the summer of 2020. We also do outreach across the spectrum, from industry all the way through higher ed to K through 12. But because we're not experts in the K through 12 space, what we do is we train the teachers in the K through 12 space, who then can take these ideas and integrate them into their curriculum. One shining example of this is work that we've done with Nate Weedham of the Metea Valley High School, where they're introducing new modules on materials design in the high school curricula. And this is work that's being done with Begum Gulsoy, who's heading up our outreach effort, and people at the Prairie School District. This is a very important part, and it grew out of some of our work with the ASM Materials Camp for high school teachers. We have a technical advisory board at CHiMaD that stretches the range of materials, going from aerospace materials to batteries and structural materials to functional materials of interest to IBM and Intel. Apple is our most recent company to join the technical advisory board, and we will be hearing from Apple later on in the meeting today, and I'm very much looking forward to the talk. And we have representatives from national labs and academia as well. So with that, I'd like to conclude. If you have any questions, please join us for the first part of the CHiMaD annual meeting. There'll be 15 minutes of a 15-minute opportunity to discuss any of these issues. You can go to our website. This is our 2019 annual report. This is open and available, and you can download this at your leisure. So thank you very much for joining us, and we look forward to seeing you at the CHiMaD live portion of the meeting next week. Thank you very much.